This week we'll be wrapping up our work in ANSYS and CFD modeling with one last real-world simulation. Today we'll be going over the process for getting this model into ANSYS, which is going to be a little bit different from what we've done in the past because this is a more organic model than we've used. What we've got here is a bamboo shark that we'll be using. This is a model that's not from a CT scan or medical data. This is a model that was digitally sculpted, probably for use as a video game asset. But it works out really well for us because, in this case, our fins are exactly in the middle of the model. We can split this model in half and use that as a plane to get a really good sense of the flow around the animal itself. This is a model that's called an STL model. We discussed this back when we were first introducing the concept of CFD. If we zoom in on this, we can see that each of these faces is a little triangle. And that's how a lot of the video game assets are set up, as these STL files. ANSYS doesn't handle STL files very well. So we'll be using a different process for importing these, and we'll make a full mesh that you'll import. So you won't have to go through the mesh construction process, but I do want to show you what's involved in that so you understand what we've done to create this. This is a program called ParaView. We use this a lot in our research because it's free and it's open source. And it pairs nicely with the other program that we use that's called OpenFOAM, which is our replacement for ANSYS for a lot of our research work. But we can first examine the model here in ParaView to get a lot of the parameters that we'll need for the simulation later on. First, going over to the Information tab, we want to make note of these values here. Note that these are all in millimeters, which will be important later on when we transfer this to ANSYS, because it's going to want to assume that this model was made in meters, so we're going to need to do some conversion. We see the bounding box of this, which would be the max distance between these and from front to back. So noting with our axes here, our x, this is the most important one, because the length of this animal, the L, is going to be this first number here. We'll round it to 512 millimeters. This will also be the characteristic length that we'll use when we calculate the Reynolds number. But I need to make note of all of these values because I need to create that bounding box, the enclosure, like we did in ANSYS, to make a box around this entire animal. So I'll note these numbers and make a box that's much bigger than this. So we'll go from, say, -800 to 800 and -300 to 300, just to make sure we've got plenty of space around the model so that we don't run into any issues with that limited domain and the boundary layers. One other thing that we will want to note about this model is that we see that from our little legend here that the shark would be traveling in the positive x direction. So that means our velocity that we need to create in ANSYS is going to have to go in the negative x direction because we want fluid to flow in this direction. Now, to start this project, I've already uploaded this geometry file, the STL file, to the CHPC. And then I also wanted to show you real quick. This is the actual bamboo shark and what it looks like in real life. This is a brown banded bamboo shark. They're small in comparison to a lot of the prototypical shark species that you see. That specimen that we have is half a meter long, which I think is about in the right range for a juvenile. The person that made that model, I'm not sure if they had scaled it to a specific size, but that size of half a meter should work out well for us. Our first thing we need to do is go over to this terminal. A lot of the stuff we do for our research with the CHPC is done on command line. So it's very, very old school, I guess you could say. The way that the simulations are set up in this OpenFOAM program is they're all run from a series of text files. The first one I want to look at is called the block mesh. This is where we'll build out that enclosure, the box around the animal. What I have to do is manually define, I've got 8 different points here, that these are the different vertices that would make up that cube. There's that one there. So these are all the vertices that I've got. And then I have to combine them down here. A note of what I'm doing is any of these double slash marks here are comments, just like how we did with R at the beginning. Because we've done a lot of these programs in OpenFOAM, this is the default box that I normally would use for something like this. But we have to name each of these faces separately because we need to define these as inlets and outlets. There's a specific order of these. If our shark is sitting in the center here, then we've got face 1, face 2 is the back, and then 3 is the front, 4 is on this side, 5 is on the bottom, and then 6 is on the top. So similar to the other simulations that we've been doing, 2 is going to be our outlet. And then I'm going to make all of the rest of these inlets. So 1, 3, 4, 5, and 6 are all going to be inlets. And they're all going to have a velocity in the negative x direction. But we'll define that in ANSYS. For right now, we're just defining these as faces, and these numbers here are the different vertices, the different points on the corners that each of those faces is going to use. Now that we've got this block mesh file set up, let's go ahead and run it and see what kind of results we get. So I can quit out of this and back to our main directory and run block mesh. And there were a couple other things in that file that I'll tell you about here now too. So we created a box with 6 internal faces, that same box here. But what we've also done is we've split this box up into smaller boxes. So we've got a total of 112,000 cells. So what I've done from a couple of other parameters in there is I've split, say, this direction up into 80 different sections, and here is like 40, we'll say, so that there's little subdivisions and even smaller cubes. This is the part of the meshing process that we also would have done with ANSYS. But that creates a problem with our shark that's in the center here, because wherever the cubes are and the shark is, they'll intersect, and we can't get good information on what's happening, say, like right at the surface of the shark, if we've got a full cube that sits on like the outside of the skin and the inside. So the next step that we're going to run is something called Snappy Hex Mesh. What it does is it takes those cube elements that are right near the surface and it slices them to conform them to the surface of the skin. This is equivalent to the Boolean process that you did in ANSYS, so that we get rid of everything that's inside of the shark and we're just left with this exterior volume. Snappy Hex Mesh takes a lot of computational power on the CHPC. So what I'm going to do is, rather than just running it like I ran BlockMesh, we're going to run a script that splits out the program into 32 different processors. So equivalently, we're going to run this on 32 different computers, and I timed this out before, and the process should just take about 30 seconds in comparison to taking, we'll say, 10 to 15 minutes. So let me show you what that script actually does. It's called a slurm file, which is something like Simple Linux Utility Runtime Manager. A lot of these old Linux programs have very interesting acronyms. So up top, I set up how I want to run this from the CHPC. So I'm running this on our research account. I have to set up the location of where all my files are. I have to set up the number of processors and where this is running from. Then I actually have to load OpenFOAM as a program. It's not, with Linux, they're not really pre-installed programs. It's something where the program is available on the supercomputing cluster, but I have to activate it each time I log in, and that's what I'm doing here. Then we split the program out into 32 parts, and then we run Snappy Hex Mesh, and then we reconstruct those 32 different parts into one single program again. So I'll close that, and I need to run a program called sbatch. This is the Slurm batching process. And one of the downsides with Linux is I can't see what's going on very easily. I've got to run some different commands to know where the process is running and what's going on in the background. So I can run sq with my unit. To see that that Snappy Hex Mesh is running. It's been running for 30 seconds, and it's got this node that it's running on Notch Peak. You'll also see that from that, it shows that I am logged in the on-demand version, because I'm also in ANSYS right now. I can see that I've been on there for 20 minutes. Now, what we always do with programs that run a long time with Snappy Hex Mesh is, while they're running in the background, we have them run a log file, which will output all the data that is being created, so we can always check on the progress. So I'm going to look at the log file snappy hex mesh. And I can see that now this finishing paralyzing parallel run, so it's run on the CHPC already, it's done. And this program ran in just 20 seconds. Because this mesh is relatively simple, this is a quick process, but for some of our more complex meshes for research, that program might run for a couple of hours. Next, let's take a look at the data that we've actually created so I can show you what this process has done so far. So I need to run a command called foam to VTK, and this VTK stands for Visualization Toolkit. It's a standardized file format that we can then load up in that ParaView program to take a look at what has been created from the Snappy Hex Mesh process. So I think I've already downloaded that separately, so we can load that up. I'll get rid of the STL file I had in there. And then I'm going to load up the VTK file that I've just created. And initially, it just looks like a box, where we've created a box, but this is the outside bounds of it. So I'm first going to create a clipping plane here, just in the center. And we see there is a hole there, so it looks like we properly created the internal geometry. And I think I can move this plane out, and you can see that that's the surface area of the shark. But to get a better view of what this actually looks like, I'm going to switch this over to surface with edges. And now you can see that we can see the interior of the shark. It's all just blank space. But we have all of the cubes, the volumetric elements that we'll use in ANSYS that are on the outside. And just like before, we have these boundary layers where very close to the shark we want smaller cubes to better capture the more complex flow patterns that are happening right around the surface. And then as we get further and further out, we don't need as much resolution, so those elements get a little bit finer. Now that we know that this process worked, we can close out of ParaView, go back to our terminal that's attached to the CHPC, and we'll run one more command here called foam mesh to fluent. And then this will create something called a .msh file, which is a mesh that contains all of those volumetric elements. It knows the names of the boundaries that we've got, all the different faces for the inlets and outlets, as well as that interior surface of where that STL file has been taken away. So now we can load this up into ANSYS, and we can continue our analysis over in there. Now I'm back over in the on-demand page for the CHPC. This will look familiar to you. And I'll launch my workbench here. And now I can drag over the fluid flow. And we want to make sure it's just fluid flow fluent, not the fluent with fluent meshing and fluent solver that we had used initially. And I'm going to skip over the geometry step and right click on the mesh and then import the mesh file. I've already got this set up from the right spot. This file will be on Canvas for you. So I can open that up, and we've got the imported mesh that's been checked. And now let's make sure that that imported by looking at this in the setup step. Just like always, we'll want to run this in double precision. take a little bit to run. And now, by default, we just have this cube. It's a little hard to know what's going on. Same thing as when we loaded this up in ParaView. Let's show you a trick that I didn't show you in the past before. In our domain here under Mesh, we can go to the Display tab, and we can click all of these to either select or unselect them. The main ones here to look at is face 2 and 3. I know that the face 3 is our front and face 2 is our back. So if we hit display, we can see that we've now got the proper mesh in here. And then now we can start to play around with the boundary conditions and get our simulation all set up. One thing we will have to do before we get too far into here is remember that in ParaView, I told you that those units were in millimeters. So ANSYS by default will work in meters. So we're going to want to scale this to make sure that we're in the right units. Otherwise, it's going to assume that this is a 500 meter long shark, which is maybe a little bit too big for what we're talking about. So let's go up to scale here. And as long as we say that our mesh was created in millimeters, then we can scale this. So now it's divided all of our domains here effectively by 1,000. And this is more familiar to what we're looking at is, we're looking at a 1 meter long domain rather than a 1 kilometer long domain. With how the walls or the faces here were named in OpenFOAM, it thinks all of these are going to be walls. So the first thing we've got to go through and do is open up our outlets here, and we're going to need to make sure and change all of these, the type, to velocity inlet, apart from face number 2, because face number 2 is this rear face, and we want that to be a pressure outlet, which it says it's the proper one there, yeah. Okay, so now we've got all of our inlets, and you'll be running this at a couple of different inlet velocities, and I might not specify that in this video, but that'll be specified in the instructions that go alongside of this. Just like before with the other simulations, we generally want to start to go down the list one by one to adjust all of the settings that we need to. Again, we don't need to worry about changing anything in the models here. We can keep our viscous turbulent model for this simulation. That we had to change that one for the blood flow because the specific model or the non-Newtonian method we used wasn't valid if we didn't change this. But we can allow for what's called viscous turbulence in the fluid in this setup. We do, however, want to go through and change our material because we're not, the shark is not flying through the air. We need to change this back over to water like we've done before. Copy and close. And then we need to change our cell zone, the fluid here, back over to water as well. Now I'm going to go ahead and save this project at the moment just to make sure that I don't lose any info. So we're looking at this one right here. Okay, and then I can go back and continue on in the setup. For my simulation here, I'm going to run at 0.1 meters per second for the velocity. But for your homework, you'll be running at a couple of different velocities, so don't worry about doing it this way. Follow the document that we're posting alongside of this. The main thing to look at here is because we want our velocity to go in this negative x direction, rather than having these being magnitude, we want to switch over to components. And we're going to look at all in the x velocity. So I'm going to run at minus 0.1, and I need to do this for all 5 of these faces. Okay, let me just double check to make sure that got listed correctly in all of these. Okay, and then I'll double check my outlet. This should be fine with the defaults. We just want to make sure we're still running it at 0 gauge pressure for that outlet. Let me turn on these faces again. And we can see the blue arrow here doesn't necessarily indicate the direction of flow. It's just saying that the blue is referring to this as being an inlet and the red arrows being an outlet. So we could have set all of these 4 walls that surround it as walls rather than velocity inlets. But if you remember that first simulation that we did, when we looked at the cross section from this direction, we had some boundary layer issues at the walls because it wanted to do the same thing that it did with the sphere in the center, where it actually was flowing fluid alongside that wall, and so boundary layers would build up at the walls here. If we set this to a velocity input, it makes sure that all the way up to the wall, it's going to run at that same velocity, and we don't have to worry about a boundary layer building up. We have 2 more things that we'll want to do here in the setup before we initialize in, well, 3 things actually that we'll want to do here in the setup before we initialize and run our solution. The first thing will be in our report definitions. We'll want to create a new force report to look at the drag, just like we've done in the past, on the bamboo shark. And we should be good to use a force vector in the x direction of 1. If we end up with a negative number for that drag coefficient, then we'll just use the positive version of that and get rid of the negative sign, and it should be the right number. So hit OK there. And then up here in our boundary conditions in internal, no, it's in the wall, sorry. What we want to do is we want to take a look at how surface roughness will affect the amount of drag that is experienced by the shark. We had talked earlier about the effect that the dimples have on a golf ball of reducing drag. We'll want to run the simulation. We'll run simulations at a number of different Reynolds numbers and a number of different surface roughnesses, so it should be 4 simulations in total, 2 of them with no surface roughness, and then 2 of them you'll run a surface roughness of 0.0005 meters. This means that it's going to have an average height of the bumps on the surface of the shark skin at 0.5 millimeters, which should be a good value that is comparable with what we would really see on shark skin. So we can apply and close there. And then we also want to go into, we can initialize our setup. And then before we actually run our calculation, we want to go into our data file quantities, because we'll want to grab a couple of extra things here, because they might want to analyze these things later on. So static and dynamic pressure along with total pressure. We obviously want all of the velocities. And then we're going to want our vorticity settings as well. We can hit OK there. And then now we should be okay to start our simulation. We'll use a max number of iterations of 200. Depending on the Reynolds number that we end up with, if our simulation is either in laminar or turbulent flow, these time steps may never converge. So like those residuals that slowly go down, they may never reach a point that will completely stop the simulation. It may go down and start to kind of oscillate a little bit. But after 200 iterations, we should be getting close enough to the real answer that our results will be good enough for what we need. Next, I'll run this simulation, and I'll speed up the time just so you're not sitting here, and we'll see if at the velocities that I've chosen, if we ever get convergence in this setup. In this case, we did get a solution that converged, so it got down to our 1 to the 10 to the minus fourth for continuity after 122 steps. When we do this with very high velocities, because we're operating in a turbulent versus a laminar flow regime, those solutions are less likely to converge with this model, but they should get close enough to a solution that's going to be acceptable for this setup. After our simulation's done, before we move over into the CFD post routine, we'll want to go into our report definitions and get the value for the drag coefficient. Because the drag coefficient is going to change probably just a little bit with surface roughness, you'll want to use this full number here with all of the digits. You notice that I do have a minus sign here, so our drag coefficient probably should be, we'll report that in the negative x direction instead of the positive x direction. A little note for when we run these simulations with a very high Reynolds number is that our drag coefficient is going to go up quite a bit. And that's because the coefficient of drag is going to be a function of velocity squared. So I'm starting at 0.1 meter per second. If I go just to 0.2 meters per second, theoretically my drag coefficient, or the amount of drag that I'll experience, is going to go up by a factor of 4. So if I go to 1 meter a second, then since I'm multiplying this by 10, our drag theoretically could go up by a factor of 100. So you see how important being aerodynamic and having low drag can be for animals if they need to travel at these very high velocities, because they have to overcome so much more drag as their velocities increase. Now let's move over to the CFD post. And we're only going to do one small thing in here because you're going to have to run this 4 separate times. Those 2 different velocities, and then with and without surface roughness. So again, we see just the wireframe model. I'm going to take that off and just put on the bamboo shark model. The one thing we're going to want to look at here is we're going to want to look at what happens behind the shark. Just like in the carotid artery, we had those secondary flows that have these counter vortices that are in 2 different circular patterns. We're going to want to take a look at those for this as well. So the way that we do that is I'm going to add in a plane, and we need to make sure that this plane is going to be in the YZ plane. I'll hit apply here, and that's going to put it in the center by default, but I can move that with this second slider here, and we're looking at probably about minus 0.2 meters. No, a little bit further. Maybe 0.3. So we want to make sure that we're pretty close to the tail of the shark. So now that we have that plane, I'm going to add in these velocity vector on that plane. Velocity. And I want to make sure that my location here is the plane that I've just created. We're looking at velocity. And for projection, I want to do tangential. See, if we do no projection here, it's going to show us the velocity coming out of the plane in all directions. But what we're really looking for is we're looking at what the velocity patterns are on the surface, because we're going to want to look for these circular vortices to see if they show up and how they'll differ at these different velocities that we're dealing with. And I'll apply that here. Now these ones are pretty small because the tangential velocity, the vortices are moving much slower than in comparison to the speed in the x direction. So I'm going to take and increase my symbol size here to a level where we can really see these patterns. Should be good enough. Now we'll want to get screenshots of all of this. So I'm going to take off the model itself and align this. And you notice that our Z is our upward direction, so it's rotated this 90 degrees, but that should be fine. Then if you want, you can adjust a couple of these different settings. Go a little bit bigger here. We also will, on the plane itself, let's double click on the plane and change the color of this so that it works a little bit better with all these arrows. Let's see if we can do black. Yeah. Now that actually will show us. So if we think, because of the Z direction is this, the top, the shark is this direction, And the shark would be placed here, coming out of the screen in our direction. So we can see that behind it we have these two counter-flowing vortices, and you'll want to get a screenshot of this at all four of those situations. So low Reynolds number with and without surface roughness, and a high Reynolds number with and without surface roughness. And that, alongside the drag coefficient numbers, will be what you're turning in for this part of the homework this week. It's a relatively light week because you'll also have a cumulative homework that goes alongside Dr. Farmer's lectures that she's gone through already.